Have you ever really thought about what infinity means?
It's really hard to wrap your head around.
It's almost like inherently kind of a paradox. We're going to be looking at some arguments that suggest that maybe infinity doesn't even make sense. And so prepare to go on another journey of discovery and disbelief on the Karma Peony channel. Karma Peony. So where does this idea of an end of infinity contradiction even come from?
Believe it or not, the seeds of this idea were planted all the way back in ancient Greece.
Ancient Greece.
Yeah.
Okay.
Let's take a trip back to around 500 BC.
Okay.
They realized that the square root of 2 can't be expressed as a simple fraction. It's what we call an irrational number.
Okay, so an irrational number is just a number that goes on forever without repeating.
Exactly, and that's the thing, it goes on forever. So to represent the square root of 2 on our number line, we're going to have to keep adding line segments for each new digit in the decimal expansion. Now, if we're saying this number, it's made up of infinitely many parts, each one a little segment on a number line, where did that last segment go?
Well, it can't really have a last segment, right? Because by definition, it's infinite.
Exactly. And that's the heart of the contradiction. The idea of infinity, it means there can't be a last anything. But if all those parts are already there, static, complete, then logically, shouldn't there be a last one? So instead of questioning the existence of the square root of 2, they just decided it must exist as a new kind of number.
So they just kind of accepted it.
Yeah.
Okay.
Let's fast forward a few centuries to around 300 BC.
Okay.
And meet another giant in the world of mathematics. Euclid? He's famous for writing elements.
Euclid, the father of geometry.
He defined a point as that which has no part.
That which has no part.
It almost sounds like saying it is a thing that is not a thing, right?
Yeah, a little bit.
A trivial contradiction, wouldn't you say?
Yeah, but I guess if you think about it visually, it's just like a tiny dot.
That's how we usually visualize it, but Euclid's definition goes beyond the visual.
Okay.
He's getting at the very essence of what a point is. If a point has no size, how can any number of them, even a finite number, let alone an infinite number, make up a line? This is like Geometry 101, and it doesn't hold up.
Wow, that's a pretty bold statement. How do we deal with this? How do mathematicians deal with this idea that a point doesn't actually have a size?
They developed a system called formalism. It's a way to represent these abstract mathematical ideas using symbols and rules. And so with this point and line problem, they use these things called intervals and unions. So instead of thinking about the point itself having no size, they say, okay, well, let's just talk about sections of a line.
Sections, okay.
Yeah, and we'll call those intervals. So for example, if you have a line that goes from 0 to 1, an interval would be all the numbers between 0 and 1.
Okay.
And they use brackets to indicate whether those endpoints are included or excluded.
Right.
So a square bracket means the endpoint is included.
Okay.
And a parenthesis means it's excluded. And then you can have different types of intervals. You can have what's called a closed interval.
Okay.
Where you include the endpoints.
Okay.
So you would write that with square brackets. Or you can have an open interval where you don't include the endpoints.
Okay.
And you use parentheses for that.
So it's a way of being super specific.
Yeah.
What's included and what's not included.
Exactly.
Yeah, I remember this from school. So bracket, 0, comma, 1 bracket.
Yes.
Would mean the line segment includes both 0 and 1.
Exactly. And parenthesis 0, comma 1 parenthesis means all the numbers between 0 and 1, but not 0 and 1 themselves. And then unions is just a way of combining different intervals.
Gotcha.
So you use the symbol U for that, and we use unions to connect those intervals, showing that they're all part of the same line.
Okay, so it's a way of kind of sidestepping the problem.
Yeah.
Of points not having size.
Yeah.
We just kind of talk about these chunks.
Yeah, we'll just talk about the chunks.
Okay.
And not worry about the individual points.
Interesting.
But the problem is that doesn't really solve the problem.
Right.
It just kind of
It's pushing it under the rug a little bit.
Yeah, it's pushing it under the rug.
Okay.
But here's where it gets weird. What about an empty interval? How can you have an interval with nothing in it? It's strange.
Yeah.
And then to make it weirder, when we consider the empty interval and the interval of all real numbers,
Okay.
both can be seen as both open and closed.
Wait, how can something be both open and closed? That seems contradictory.
That's exactly the point.
Okay.
These peculiarities are signs that something's not quite right, It's like mathematicians are using symbols and rules
Right.
to sidestep these deeper questions.
So it sounds like even with these formal systems, we still run into these logical inconsistencies.
Exactly.
Okay, I see how these ideas are all kind of like connected.
Yeah.
But how does this lead to the end of infinity contradiction?
To understand that, let's go back to our idea of infinity as a collection of things, all existing at the same time.
Okay.
Let's try and visualize the square root of 2 on a number line. Imagine dividing the number line from 0 to 2 into segments, where each segment corresponds to a digit in the square root of 2's decimal form.
Okay, so we'd have a segment for 1, then 0.4, then 0.01, and so on.
Yes, and remember this is an infinite expansion, so we have infinitely many segments. Now add one final segment representing the interval from the square root of 2 to the number 2. Remember, we're working with the line segment from 0 to 2.
So we've divided up this line segment from 0 to 2, representing each digit of the square root of 2 with a final section from the square root of 2 to 2. I still don't quite see the contradiction.
Well, the contradiction arises when you consider that if this decimal expansion truly represents a completed infinity, then there must be a last segment before the final one that goes from the square root of 2 to 2. The key to this whole argument is we're assuming all those intervals, every single one, they all exist at the same time.
Wait, all at once. Not like one after the other.
All at once, already there, the whole set. Now, if those intervals are truly infinite, meaning there are infinitely many of them, there shouldn't be a last one, right?
Yeah, I mean, how could there be? If it's infinite, there's always one more.
Right. But here's the catch. Those intervals, they're all in order on the number line, right?
Yeah, they have to be, leading up to the square root of 2.
Which means there has to be a last interval before you hit the actual square root of 2. If there's always a segment before any given segment, how can there be infinitely many segments?
It's like you can't have a last brick in an infinitely long wall, right?
It just doesn't logically follow.
This whole idea of infinitely many parts, it's fundamentally flawed, right? It leads to these logical contradictions.
Precisely. A completed infinity where all the parts exist at once, it's just not a logically sound concept.
Don't mathematicians have ways of dealing with this already?
Well, yeah, they do, but it's not a real solution. They often argue that the rules of formalism, the way they've set up their mathematical system, don't allow for this contradiction to be expressed formally. Therefore, they say it doesn't exist within their system. Mathematicians basically create rules within their systems that stop you from even expressing this contradiction in their language.
It's like they're saying, you can't talk about the problem if you use our words.
It does kind of seem like that, yeah. This doesn't actually solve the underlying problem, it just prevents us from talking about it within their specific system. It's like trying to ignore the elephant in the room and hoping it'll just go away on its own.
Yeah, that doesn't sound like a very solid approach. But wouldn't that mean we could just create a different formal system? One where this contradiction can be expressed?
Precisely.
Are there any alternative approaches out there?
Absolutely. Some mathematicians have proposed redefining real numbers, like the square root of 2, as algorithms.
Like who?
Well, like, Jules Richard,
Go.
Alan Turing.
Oh, wow, Turing, the computer guy.
Yeah, and more recently, Dr. Doran Zielberger.
Okay, so this isn't just some fringe theory.
No, not at all. Real numbers, like the square root of 2, could be seen as algorithms that calculate their decimal expansions rather than fixed, complete values. Dr. Zielberger even called pi an equivalence class of algorithms.
Meaning there are many different ways to calculate it, but they all lead to the same, result. So are we saying that, like, infinity just doesn't work?
Yeah.
That it's impossible? Like, how can there be infinitely many of anything?
Yeah, it really makes you question, like, the whole concept of infinity.
It does. Like, maybe this idea of endlessness, maybe it just doesn't work,
That's a question that's gaining more traction these days, especially with the argument that everything in the universe might actually be granular.
Granular, okay. What exactly does granular mean?
So imagine you're looking at a smooth line, right?
Okay, got it.
But what if when you zoom in, really, really zoom in, it's not smooth at all?
Okay, I'm listening.
What if it's actually made up of a bunch of tiny, indivisible points? Kind of like a chain with super, super tiny links.
So instead of a continuous line, it's like a series of, like, discrete points all jammed together.
Exactly. And that's the essence of granularity. The idea that everything, even space and time, could be made up of these fundamental units that can't be broken down any further.
Okay, so how does that tie back to infinity?
Well, think about it this way. If everything is ultimately made up of a finite number of these tiny building blocks, then how could anything truly be infinite? So even if the universe is unbelievably massive, if it's ultimately granular, it still has to have a limit, a boundary somewhere.
So no matter how big the universe is, there's an end to it somewhere.
That seems to be the logical conclusion, yeah. And it's not just about size. Think about time. We tend to imagine time as stretching on forever, but in a granular universe, time would also be made up of these fundamental units.
Okay, so you're saying there's like a smallest possible unit of time, like a tick-tock of a universal clock. And there's only a certain number of those ticks, even if it's a mind-bogglingly huge number.
Precisely. There are some pretty compelling arguments and observations that point towards a granular universe.
Oh, really? Like what? Give us an example of why this idea is gaining traction.
Sure. One of the most interesting arguments comes from looking at how things move. Have you ever considered that movement as we perceive it might actually be an illusion?
Wait, what? Like, you mean the way a flip book works, where it's just a bunch of still images that trick our eyes into seeing movement?
Kind of, yeah. Think about Zeno's paradoxes, those ancient Greek thought experiments that have puzzled philosophers for centuries. One of them suggests that you can never actually reach a destination because you always have to first cover half of the remaining distance.
Oh yeah, I've heard of that. It's like saying you can't walk across a room because first you have to walk halfway across, and then half of that remaining distance, and then half of that, and so on. It's like, how do you ever actually get there?
Exactly. It's a bit of a brain twister. But here's where it gets really interesting. If we assume a granular universe where everything is made up of these indivisible units, Zeno's paradox completely falls apart.
Wait, really? How does a granular universe solve that problem? Help me wrap my head around that.
Well, if there's a smallest possible unit of space, at some point you're going to take a step that covers that entire unit. And boom, you've reached your destination. No more endlessly halving the distance because you've hit that fundamental limit of how small you can go.
Oh, I see. So in a granular universe, movement wouldn't be this smooth, continuous flow that we think of, but rather it would be a series of super tiny jumps between these fundamental units of space.
Precisely. And that starts to really challenge the idea that anything, including motion, can truly be infinite. It suggests there's always a limit, a smallest possible unit, even if it's incredibly tiny. It's a real challenge to our intuition. We're so used to thinking about things going on forever, but maybe that's not how reality actually is.
So it's not just numbers and lines anymore.
Right, and it makes you wonder, what are the implications? Because infinity pops up everywhere, right? I mean, think about the universe, or even those tiny particles physicists talk about. It really challenges our understanding of how the universe works at the most basic level.
So maybe infinity isn't a thing at all. Well, what do you think? Would you ever draw your own conclusions and dare to question the mainstream beliefs? This has been another journey of discovery and disbelief right here on the Karma Peony channel. Thanks for joining us.